Okay. Today we shall discuss about the derivative. The definition and the use of the derivatives in the study of real functions. So we shall work with functions defined on intervals of the real line. So I, it's an interval included in the set of real numbers. And we shall take up an element in I. So we shall consider the following limit when x tends to a of f of x minus f of a over x minus a. Well, now, there is a geometric interpretation of this limit. If the graph of the function it is, let's say this one, and if a is a point somewhere over here, the geometrical problem, a problem in classical geometry is to find that straight line which pass through this point whose coordinates are a f of a. This is the point on the graph of the function, and to find the straight line which is the closest to the graph of the function which approximates, is the best approximation of the graph of the function around the fixed point on the graph. So the idea, which goes back to Fermat, for example, is to take another point x in the domain of definition. So the point of the graph has the coordinates this time x, f of x, and consider the straight line which pass through these 2 points. More precisely, the slope of this line is, of course, the ratio f of x minus f of a over x minus a. And now, if x is closer to a, of course, this number is closer to the slope of the tangent line. So finally, the slope of the tangent line is given by this limit. And now the definition is that we say that f is derivable at the point a if this limit exists and is a real number, so it's not infinite. Exists and belongs to R. If this is the case, then the value, we denote the value of the limit with f prime of a, and we call it the derivative of f at the point a. So it's a number. Consequently, the equation of the tangent line will be y minus f of a equals the slope, which is f prime of a, times x minus a. Okay, according to this definition, an approximation around the point f is obtained. So if we consider the polynomial function, call it t1 of x equals f of a plus f prime of a times x minus a, this is the so-called linear approximation of f around a, which is a function, which is a polynomial of the first degree, which has the following properties. At the point a, it equals f and also its derivative, which are obvious properties. Okay, so now the derivative is the most important tool in the study of functions. What do we mean by a study of function? To study a function, of course, if we think to the graph of a function, there are intervals on which the function is increasing, like here, then it is decreasing, then increasing again, and so on. According to this behavior, there are some special points on the graph for example, this one and this one here, call them x1 and x2. What happens at x2, at x1? Around this point, the value at x1, it is the greatest value, while at x2, it is the least value around that point. These are extrema. So when we discuss about the study of a function, we mean the monotony and to find the local extrema. Okay. The monotony is given by the sign of the derivative. If we think to the geometric meaning of the derivative to be the slope of the tangent line, and the local extrema, let's give the definition. So A is a local minimum if there exists a positive R such that f of x is greater or equal than f of a for every x in the interval a minus r, a plus r. A local maximum means that f of x will be less or equal than f of a for every x in the interval a minus r, a plus r. Okay, so we have local extrema, which can be local minimum or local maximum. To study the function means, first of all, to find the intervals of monotony, where is it increasing, where is it decreasing, and to find the local extrema. So the monotony is given by the sign of f prime, and of course the local extrema will be given by the points where the derivative then change the sign. This could happen at points where the derivative is 0, or at points where the derivative doesn't exist, so f has not a derivative there. We shall see examples. Let's consider, for example, the function f of x equals 2x over x squared plus 1. It is defined on the set of real numbers, taking values in the set of real numbers. So in order to study the monotony and find the local extrema, first we need to compute the derivative. Which is given by this expression. So it gives us 2 times 1 minus x squared, and below we have x squared plus 1 squared. Now we find the solutions of the equation f prime of x equals 0, the roots of the derivative. In our case, it means 1 minus x squared equals 0, so we have 2 points. These are called critical points. So the points where the derivative vanish are called critical points. And now we fill in the following table, in which the most important information is the sign of the derivative. So our domain is minus infinity, infinite. We put here the critical points. Yes. And now the sign of the derivative. So the sign of this function will be negative, positive, negative. So the conclusion is that on the interval minus infinity minus 1, the function is decreasing. Then on minus 1, 1 is increasing, and then it is decreasing again. We compute the values of f at minus 1 at 1, and at 1 they are, here it's minus 1 and here it's 1. And in this moment we have the answer to our questions. X equals minus 1, it's a local minimum. X equals 1, it's a local maximum. And the monotony is, as we can see it in on this table, so on the intervals minus infinite, minus 1, it is decreasing. On 1 infinity, it is decreasing, and on minus 1, 1, it is increasing. To fulfill the complete study of the function, it's worth to compute also the limits at minus infinity, infinite, which in this case are very simple. They are both 0, and also we can sketch a graph which is given by the following. Okay, it's a sketch, not very clear. Here, the graph passes through 0, through the origin, because f of 0 equals 0, and it goes like this. Okay, we do not enter into details about asymptotes, whatever, because we are interested in monotony and mainly in monotony and extrema. Let's consider another example. For example, we can study for even more complicated functions. Let's consider, for example, f of x equals logarithm of x over x. So here the domain of definition is 0, infinity. We compute the derivative, which is 1 over x times x minus logarithm of x, which means 1 minus logarithm of x over x squared. Now the critical points are given by this equation, which means logarithm of x equals 1. So we get one single critical point. It's x equals e. And now the table of variation of the function. So this time the domain is 0, infinity. The critical point, we have one single critical point e. Now, the sign of the derivative, it's obvious, here is positive, here is negative. So the function will be increasing and then decreasing. The value at e equals 1 over e. So here we have. So in this moment we have the monotony. It is increasing on 0 e and decreasing on the interval e infinity, while x equals e, it's a local maximum, but actually it is a global maximum because the value here is the greatest value of the function, as the table shows, the variation table shows. One can compute also the limits at 0 here of logarithm of x over x. That is minus infinity over positive 0, because we close to 0. X tends to 0 through positive, so it is minus infinity. While the limit at infinite, it's infinite over infinite. One can compute it by using the L'Hopital rule, which is 1 over x, 1 over. So it's 0. So here is 0. As you can see from this table, indeed, the value of f at e is the greatest value. So actually, we prove the following inequality. Logarithm of x over x is less or equal than 1 over e for every positive x, among other informations included in this table. Again, we can sketch the graph of the function. The function is defined only on the right of the vertical axis, and it starts from here. It goes to the value at e is 1 over e, and then it goes to the horizontal asymptotes, which is the horizontal axis. So the graph, it is approximately like this. Okay.